Okay, gentlemen, today is Wednesday, May the 13th, and today we are going to continue our discussion of waves um, with lesson 105. I can't believe that that's possibly true, but we'll see. But this one is all about light. All right, we've been talking about waves for a week or so now, and yesterday in the last video we talked about sound waves specifically. Today we're going to start a 2 or 3 day discussion of waves of light. Okay, now light is very similar to sound in terms of its behavior. It echoes, it reflects, it refracts, it diffracts, and so on. But light has some very exceptional properties as well. Whereas sound is a mechanical wave that cannot travel through a vacuum, light is actually an electromagnetic wave, and it can travel through a vacuum. This is why we can see the sun and the other stars that are out there in the solar system. So, what exactly is light? Well, light is part of the electromagnetic spectrum. And this is a diagram of the electromagnetic spectrum. And I want you to understand that light is only is only a very tiny portion of the electromagnetic spectrum. All right, you can see it as soon as it pops up here, but you can see it here. All right, this is visible light. This is the electromagnetic waves that we can actually see. And if you look further down, you've got gamma rays and X-rays, ultraviolet light, infrared light, microwaves, radio waves, and they're all there. This, by the way, there's a copy of this or another example of this on your handy dandy little reference tables on, believe it's the second page. Yes, the second page. But there it is. And so the whole electromagnetic spectrum is shown there. Notice that here, from left to right, the wavelength is getting bigger, right? We start out with a little wavelength here and a big wavelength here. And what that means is that because the speed of light is constant, right? The speed of any wave in any medium is constant. That means that the frequency is, for crying out loud, the frequency is actually getting smaller as we go from left to right. Okay, so on this side, we've got a short wavelength and a high frequency. I don't know if you can make that out there. And on this side, we've got a long wavelength and a low frequency. Okay, but visible light is just this tiny little portion right here in the middle. All right, so what do we know? Well, we know that visible light is part of the electromagnetic spectrum that can stimulate the retina of the human eye. Now, be aware that other organisms, certain insects and other animals, actually can see different parts of the spectrum. And so what's visible to us is not visible to them, and what's visible to them is not necessarily visible to us. So keep that in mind. This is a very human-centric definition of visible light. However, one thing that we can't argue about is that the speed of light is 3.00 times 10 to the 8th meters per second. That's darned fast, very fast. And this is technically the speed of light in a vacuum, but it also, air has such little density that it doesn't really change in air either. Now, this number is also available on your handy dandy reference tables. You can see it right there. Speed of light in a vacuum, abbreviated with a lowercase c, and it's 3.00 times 10 to the 8th meters per second, just above the speed of sound. Okay? And again, this is true in a vacuum or in air. Now, let's talk about the various properties of light, all right? We said already that light could be reflected, and we know that light waves follow the law of reflection. Remember that from the other day. The angle of incidence equals the angle of reflection. And so if you've got a surface with a normal line drawn to it, a perpendicular line, All right, if a light ray comes in and strikes the surface at some angle that I'll call I, then it's going to be reflected at an angle that I'll call R. And although I didn't do a very good job drawing this, angle I and angle R are equal. All right, they are the same. And that is the law of reflection for light. Now, light rays are reflected off of every surface, right? Whether it's a perfectly smooth mirror or a rough sandy beach, okay? Light is always being reflected. And so that leads us to two different kinds of reflection. The first is what we ordinarily think of as reflection, regular reflection, okay? And this is the case that when parallel light waves strike a smooth surface, their reflected rays are parallel, all right? And so I'm going to draw a smooth surface here. Oh, that was pretty good. And I'm going to change the color of the ink. And I'm going to say, okay, here's a light ray coming down. It strikes and is reflected. Okay. Then I've got another light ray. We'll make this one green. And this one's going to come down here and it's going to bounce and it's going to be reflected. Whoops. I didn't do a great job with that. And then another light ray is going to come down and it's going to strike and it's, whoops, that was terrible. But what you should notice here is that all of these light rays are parallel to one another. And if they come in, doing this with a mouse is awful. But in any event, the light rays themselves are reflected in the same direction as they come in, and so this gives us a lot of different aspects to this. All right, so think about it this way: what would happen if a bunch of parallel light waves struck a smooth surface and came back out? Well, in theory, they could then create what we would call an image. And the image itself would be, for the love of God, like so. So let's say that you've got a mirror here. All right, and I'm going to go back to my red. And here are you. You're standing in front of the mirror, okay? Now, if you want to look at your toes, what that means is that there's got to be a ray of light that strikes, and I'm going to, here's your eyeball, all right? It's going to come like so. I missed. Let's try that again. And so the ray of light is going to be reflecting this way. And so it comes off of your toes and reaches your eyes, okay? And of course, a ray of light also would go from your eyes to the top of your head. And so you can see your whole body in that image. Now, what happens is if you continue those rays, on the other side of the mirror, whoops, this is a terrible drawing. But what you'll find is that on the other side is your image. And your image is going to be just about the same as your body. All right. And so what that gives you then is what we call a regular reflection. Now, what that means is that when parallel light waves strike a smooth surface, their reflected rays are parallel. All right, I showed that in the diagram that I drew on the left. This produces what we call virtual, erect, and perverted images. Now, before you get all giggly, all right, the word virtual means that it doesn't really exist. You can't reach in and shake your reflection's hand, all right? Your reflection is not a person, all right? It's not real. It doesn't really exist, right? It's a bunch of light waves that have come together in a certain way to produce an image on your retinas. The word erect simply means that it's right side up. The image is not upside down, okay? And finally, it's perverted. And what that means is, what that really means in physics anyway, is that if you raise your right hand, okay, your image raises its left hand. All right, think about that. Go in the bathroom, raise your right hand, and look at the person that you're staring at. All right, that person is raised is his left hand. All right, that's what we mean by a perverted image. Okay? And the image will be the same distance into the mirror as the object is out of the mirror. And I've done a lousy job drawing this, trying to draw it with my mouse. But you can certainly see that if you stand in front of the mirror, your image is just as far from the mirror as you are. Okay. Now, what happens when light rays strike a surface that is not perfectly smooth? All right. Well, in this case, let's draw a rough surface. All right. It doesn't really matter what the surface really looks like. And then we're going to have...
It's 8 o'clock.
Well, thank you, Jesus. So I'm going to send down a light ray, and it's going to strike right here, and it's going to bounce almost directly back outward. Okay. Then I'm going to send down another light ray, and it's going to come in parallel, and it's going to strike right there, and it's going to bounce off this way. I shouldn't have drawn that in red. And then I'm going to send in another light ray, and it's going to strike this surface and bounce off this way. All right. Notice that the reflected rays are no longer parallel. They're no longer cohesive. And so the light literally is diffusing. It's going all over the place rather than staying together to form an image. And so the reason for this is that the normals are different because the surface is not flat, and therefore the reflected rays are not parallel. And the most important takeaway from this is that no image is formed. This is why you can't stare at a wall and see your image, and you can't stare at your desk unless your desk is made of a mirror, and you can't stare at the comforter on your bed and or your dog and see your image. Maybe in your dog's eyes, I suppose, because those are smooth. Okay, but for a rough surface, you're not going to see an image. Okay. Now, light can also be refracted. Now, we know what refraction of regular average American waves, whatever they might happen to be. And so you can certainly look at the refraction of light. And we know that light waves bend whenever they enter a new medium because of a change in their velocity. You strike a new surface or the surface between two different media, and your speed will change. Okay, and that will cause the wavelength to change, and that therefore the light wave will bend. A ray that passes into a more dense medium will bend toward the normal. Now, this is difficult to illustrate. I had a nice little fish tank in my classroom, and the best I can do here for you is a cup of water that I put a whole bunch of salt in. All right, now, this may or may not work, but if you take my little laser pointer here and shine the light ray in it, nah, it's not going to work. Oh well, it worked It works down here on my desk in the shadows, but it doesn't work there. If you can set this up in your own house, you can play with the diffraction or the refraction of light and cause your laser pointer to actually bend toward the normal. All right, it's because a ray that passes into a more dense medium like salt water will bend toward the normal. A ray that passes into a less dense medium will bend away from the normal. Okay. And this is just the same set of images that I showed you the other day when we first talked about the idea of the refraction of light. We have a boundary of some sort between two media, and maybe it's air and water, or glass and air, or something here. And the vertical lines that you see here represent the normal lines here. And so this is the boundaries, the deep, thick black line, and this represents a normal line. We have an incident ray, we have a refracted ray, and in this case, notice that angle I is greater than angle R. And what that means is that the light ray has bent toward the normal line. So that means that this side is less dense and this side is more dense. All right. On the other side, again, we've got the normal line up here, and the thick black line represents the boundary here. The incident ray comes in, the refracted ray comes out, but now the angle of incidence is much smaller than the angle of refraction. Here, we end up with this relationship. And again, that's because this is more dense on the upper side, and on the lower side here, we've got a less dense medium, okay? And therefore, the light ray is refracted away from the normal. Okay, in any event, that is a quick summary of light. Tomorrow, we're going to get into even more detail with refraction and a few other things. But in any event, have yourselves a happy day, and I will talk to you tomorrow. Oops, wrong one.